Okay, so today we're going to take some notes on section 7.1, which is on the Rational Root Theorem, or also known as the Rational Zero Theorem. So take a minute and go ahead and write down the Rational Root Theorem and the first example, and then we'll work through that example together. And I will explain what the Rational Zero Theorem means. It's a little bit hard to understand when you read what's written there, but I'll break it down and help you work through the first problem. So let's break down what this Rational Zero Theorem is saying in relation to the first example. So not all polynomials have rational roots or rational zeros. What we're looking for is, when we're looking for a root or a zero of the function, we're looking for some x value that we can plug in that will make this equal to 0. So that's called a root. If we can find an x value that does that, that's called a root or a zero of the function. And so it says that if there is a rational root or rational zero, remember a rational number is something that can be written as a fraction. So all whole numbers are rational, all positive and negative integers are rational, all fractions are rational. Okay? So if it has any rational zeros, we can write it over the form m over n. And when we write it over the form m over n, what the Rational Zero Theorem is saying is that m has to be a factor of, it says, the constant term. So that's usually the one that it's at the end of the polynomial with no variable. That's called a constant term because there's no variable connected to it. So m has to be a factor of 6. And n, it says, has to be a factor of the leading coefficient. So that means the one at the beginning with the highest degree. And so n has to be a factor of 2. So what we're going to do is we're going to list all the possibilities that m over n could be. So m over n, since m has to be a factor of 6, what are all the numbers that divide evenly into 6? Plus and minus 1, plus and minus 2, what else? Plus and minus 3. Anything else? Plus and minus 6. So the numerator could be any one of those numbers. The denominator has to be a factor of 2. Plus and minus 1, plus and minus 2. So notice that we're only looking at the first number and the last number of the polynomial, if we have it written in order with the highest degree first and the constant at the end. We're only looking at those two numbers. We don't care about the coefficients in between. And so that gives us a list of possible rational roots. If we look at all the possible combinations now, m over n could be 1 over 1, that's 1. Or it could be 1 over 2. That's plus and minus 1/2. Okay? Or if we pick the 2 on the top, it could be 2 over 1. Or it could be 2 over 2. What's 2 over 2? 1, and we've already listed 1, so we don't need to list it again. Then we get 3 over 1. We haven't listed 3 yet. And then we get 3 over 2. We haven't listed that yet either. And then what else do we need to add to our list? 6 over 1 is 6. And what about 6 over 2? We already have it. 6 over 2 is 3, and we already have it right here. Okay? So that is our list of possible rational zeros. So if there is a rational zero to this polynomial, it's got to be one of those. Zeros, I should say. Possible rational zeros. Okay, so we learned yesterday that a quick, easy way to plug a number into a function is, instead of actually plugging it in, we can use the synthetic method. So that's what we're going to do, is use the synthetic method. We're going to go through this list until we find one that turns out to be 0. And yesterday we used 2 or 3 rows to do the synthetic method. Since you did it yesterday, you probably have the hang of it now. We're just going to use 1 row to do it. So we're going to do it all in 1 row, and I think after we do the first couple together, you'll see that's actually pretty easy to just use 1 row at a time. So up at the top, we put all the coefficients of f of x. So that's 2, 1, negative 13, 6. And the first number I'm going to try is 1. We have our list of possible rational zeros. I'm going to try 1 first, because 1's a pretty easy number to work with. So if I try 1, remember what we do, we bring down the first number, and then we multiply and add. So we're going to do those 2 steps together all in one. That's why we're able to do it in 1 row. So if I multiply 1 times 2, that's 2, and then add it to 1, I get 3. Now we're going to multiply again, 1 times 3, add, and what do we get? Negative 10. Multiply and add, what do you get? Negative 4. So that one is not a 0 of this polynomial. So 1 didn't work. So now we can try negative 1. And we're just going to keep going through this list of possible rational zeros until we find one that works. So this one is, we start with the 2, multiply, and add. So that's negative 2 plus 1 is negative 1. Multiply, you get 2, add to negative 13, and you get negative 11. Oh wait, negative 12. I did negative 1 times negative 1 is positive 1. Add that to negative 13. We get negative 12. Do you agree? Okay. Multiply again, you get positive 12. Add it to 6, and you get 18. So that one didn't work either. So let's go to our next number, 1/2. Now, you can, if you want, when you're doing these, you don't have to go through the list in order. You could do all the integers first, since sometimes integers are easier to work with than fractions. In this case, it's not too bad to try the fractions, but you can always do that if you want to try all the integers first and then come back. If you haven't found one yet, then come back and try the fractions. But I'll show you how it works with fractions. So if we do 1/2, 1/2 of 2 is 1. Add it, we get 2. 1/2 of 2 is 1. Add it, we get negative 12. 1/2 of negative 12 is negative 6. Add it, and we get 0. So we just found one. We found one that works. We're trying to get a 0 at the end, and we got a 0. Okay? So now we found a root, which means we also found a factor, sort of. So the reason why I say sort of is because the factor that we would get associated with 1/2 is x minus 1/2. Now, if we were factoring a polynomial, we wouldn't usually end up with fractions like that, but it'll work out in the end. We'll see that in just a minute. So our original polynomial now can be written as x minus 1/2 times something. We know x minus 1/2 is a factor because it made the polynomial equal to 0. Okay? Now remember, we can get the remaining polynomial just by looking here. This gives us the quotient, which is 2x squared plus 2x minus 12. Now what's the first thing you notice about that, the quadratic factor, this part? Notice anything about that? You can easily factor out a 2, and we actually need that 2 to convert this x minus 1/2 into a normal factor. So if I factor the 2 out, the quadratic part becomes x squared plus x minus 6. And now that I have this 2 factored out, let's apply it to this to make it into what would look like a normal factor, 2x minus 1. And then, does anyone see how we can factor x squared plus x minus 6? X plus 3, x minus 2 would work. Now we have it fully factored. So that's what the original question was asking. It said, write the polynomial in factored form. So we have done that. We didn't list all the rational zeros yet, so now let's go back and do that. Find the rational zeros. So we found one from our synthetic division that came out with x equals 1/2. X equals 1/2 is a rational zero. Now that we see the factors, what value of x makes that factor 0? -3. So x equals -3. And what x value makes that factor 0? X equals 2. So there are all of our zeros. This is a third degree polynomial, so it can't have more than 3 zeros or roots, and this one has all 3 that are rational. So that doesn't have to happen. It won't happen every time, but for this one we got 3 rational roots, or 3 rational zeros. Any questions on that one? Okay, go ahead and try the same thing on example 2, please. Okay, so I'm going to go ahead and work through this whole thing so you can see and compare it to what you did. The first thing we need to do is make our list of possible rational roots. So n has to be a factor of 20. So that's going to be plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 5, plus and minus 10, and plus and minus 20. Now that's quite a long list, but fortunately in the denominator, we look at the leading coefficient, and it's 1. So that means we only have plus and minus 1 in the denominator. So even though our list on top is pretty long, the list in the bottom is short, and so that means we only have m over n could be plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 5, plus and minus 10, or plus and minus 20. And so then we'll start trying those using the synthetic method. Now let's see, 3, 2, 1, 0, we're not missing any terms, so we always want to check and make sure that we're not missing any terms. The powers go down 3, 2, 1, 0, so we're not missing any terms. So we have 1, 2, -19, -20. So first I'll try 1, and that is 1, multiply and add, you get 4, or actually you get 3. Multiply and add, you get -16. Multiply and add, you get -36. Do you agree with those? Then I'll try -1. Start with a 1, multiply and add, you get 1. Multiply and add, you get -20. Multiply and add, you get 0. So on the second try, I found a root. And so now I can say that f of x is equal to x plus 1, because -1 is a root, x plus 1 has to be a factor. And the remaining factor, remember, to get the remaining factor, I can get that from these numbers. Those are the coefficients of x squared plus x minus 20. And then we try to factor the second polynomial, or the quadratic part. We want to try to factor this, and that does factor. Paige, were you able to factor that?
Yeah, I got x plus 5 times x minus 4.
Good. And so that is completely factored now, and we can also see that this one has 3 rational roots. Okay, so we have our roots are x equals -1. That makes that 0. This is 0 when x equals -5, and this is 0 when x equals 4. So we, again, got 3 rational zeros. Okay, questions? Okay, this next one is a 4th degree polynomial. I'll work through that with you. So we can start our list of possible rational roots. M over n on the top. What number do we look at? The 3. Okay, so factors of 3, plus and minus 1, plus and minus 3. Pretty short list. And then for the bottom, the factors of 2, plus and minus 1, plus and minus 2. So our list of possible rational zeros is just going to include plus and minus 1, plus and minus 1/2, plus and minus 3, and plus and minus 3/2. And we need to notice that f of x is missing a term. Which term is it missing? X squared, so it's going to be 2, -1, 0, -6, 3. And I'll start by trying 1. Bring down the 2, multiply and add, multiply and add, multiply and add, multiply and add. That one didn't work. Okay, go ahead and keep working through the list. Let me know when you find one that works.
Try like using 1 and -3, so plus 1 and.
Let's see if that works.
So
1 over 3.
this factor is 0. We can actually set it equal to 0 to find out when it's 0. That would be x cubed equals 3, which x equals, if I wanted to get x by itself, what would I have to do to both sides? Cube root. So you get the cube root of 3. And so this one is a, we only have one rational root. The other roots are, this is called a triple root because you have x cubed equals a number, so that's going to be a triple root, and that is an irrational root. So we have 3 irrational roots. Do you remember when we talked about double roots, when a graph just comes down and touches a axis and comes back up? We called that a double root. When it touches twice, that would be, for example, if this was at 3, then our polynomial would have x minus 3 squared. A double root only touches once. So this would be a triple root, which means when it's an odd power, it still crosses, but it crosses very flat. So at the cube root of 3, if the cube root of 3 was right here, this graph would cross at a very flat angle. So it might look something like, let me redraw that. So it might look something like this. It would come up and go flat, cross at the cube root of 3, and then continue on up. So a repeated root with an odd power gets very flat, whereas a repeated root with an even power bounces off of the axis. Okay, that's just extra information that you don't really need to answer this question. The question was just asking you to find the rational zeros. We found that there's only one, and that's x equals 1/2. Writing the polynomial in factored form, we did that here. That's in fully factored form. Okay? Any questions on that one? Okay, one more for you to try. Okay, so some of you may still be working. I just want to check in and see how we're doing so far. So my list of rational roots only had 4 numbers, plus and minus 1, plus and minus 1/2, plus and minus 1/3, and plus and minus 1/6. So when I went through and started trying them, 1 and -1 didn't work, but then 1/2 worked. Okay? And since 1/2 worked, then we can say f of x equals x minus 1/2 times, these numbers give us the coefficients. It would be 6x cubed plus 38x squared plus 18x plus 2. And then as we've done before, we would want to factor a 2 out of all those and apply it to this factor. So it's now going to be 2x minus 1, 3x cubed plus 19x squared plus 9x plus 1. Okay? Now, we still need to factor this cubic. And you could try grouping. We learned when there are 4 terms, you can try factoring by grouping. Grouping actually won't work in this one because if you factor an x squared out of the first 2 terms, that leaves you with 3x plus 19. And then the second grouping, nothing factors out. And so that doesn't match up. Factoring by grouping is not going to work for that one. And so what do? We do the synthetic division again. We make a new list of m over n for this new cubic polynomial. So m over n for the cubic is just going to have plus and minus 1 in the top, and in the bottom plus and minus 1 and plus and minus 3. So that's going to be plus and minus 1 and plus and minus 1/3. Okay? Now listen carefully here. We already plugged 1 in when we had 1 on our original list, and that was the first thing we tried here and here, 1 and -1. Neither one of those worked. We don't need to try them again, because if 1 didn't make the big polynomial 0, then it's certainly not going to make a part of that 0. So we don't need to try 1 again. So we can go right to 1/3 and -1/3. So now my new table is going to have 3, 19, 9, and 1. And we'll start with 1/3. That is 1/3 of 3 is 1. Add it, you get 2. 1/3 of 2.
Wait, don't you get 20?
Oh, sorry, that's 19. I was thinking that was a 1. So you're right. It's a 19. So when I add, I get 20. Now when you take 1/3 of 20, it's going to get a little messy. We get 20/3. And we're going to add that to 9, which is 27/3. So we get 47/3. And then if we take 1/3 of that, we're going to get 47/9 plus 9/9 is 56/9. Definitely not 0. Okay? So now let's try -1/3. Multiply by -1/3 and you get -1 plus 19 is 18. -1/3 of 18 is -6. Add that to 9 and you get 3. -1/3 times 3 is -1. Add that to 1 and you get 0. So now we know that f of x can be written as our original factor, 2x minus 1, and then this cubic polynomial can be written as x minus 1, or actually x plus 1/3 times, those numbers give us the coefficients for that factor, which is going to be 3x squared plus 18x plus 3. What do you notice about that new quadratic? It's got, they all have factors of 3, which we want to apply to this middle factor, so it becomes 2x minus 1, 3x plus 1, and x squared plus 6x plus 1. Okay? Now, see if you can factor x squared plus 6x plus 1. What numbers can you multiply to get 1 that add up to 6? What numbers multiply to get 1 and add to get 6?
1 and 1, wait. Only 1 and 6. 6 and 1. Oh, wait, no. No, never mind.
Okay, there are none. You can't. The only two numbers you can multiply to get 1 are 1 times 1. And those, you can add them or subtract them, they're never going to give you 6, so it will not factor, which means we're done. This is in factored form. Okay? We got a rational 0 out of this, that's x equals 1/2. We got a rational 0 out of this, that's x equals negative 1/3. Okay? So those are the only rational zeros because this other quadratic is not factorable. So we've actually finished the problem. But this is a 4th degree polynomial. So what are the other 2 roots then? They're definitely irrational. They could be real or non-real. We could tell by taking this third factor here. When is x squared plus 6x plus 1 equal to 0? If it's not factorable, what can we do? Quadratic formula. So if you take your calculator out, I gave you that nice fancy program so you can run the quadratic formula and enter in 1, 6, 1. Okay, so the discriminant is 32, so we get negative 6 plus and minus 4 root 2 over 2. That's negative 6, or that's actually negative 3 plus and minus 2 root 2. And so we see that they are real, but they're irrational. So this gives us 2 real irrational roots. Okay, that was a bonus. The problem wasn't asking for that, but now we can kind of see the big picture. We see that when it's a 4th degree polynomial, it's got to have 4 roots. If 2 of them are rational, the other 2 have to be irrational, which might mean they might be non-real also. Okay, and that completes our notes for 7.1, or was it 7.1? 7.1?
Are those the last notes for the whole day?
I think they are.
Yeah! We did it!